Hello Legacy students, Marsh here. So today we're going to start graphing quadratic equations. We're going to embark on a new adventure in math, aka we're going to get curves today. So that's going to be tons of fun. You're going to want your notes and then those two foldables or those two pieces of paper I gave you in class as well. Learning objectives for today. What do you want to be able to accomplish by the end of this video? You want to be able to graph a quadratic equation that is in standard form. And you also want to be able to identify key features of a graph, which the second learning objective you've done before, but I'm going to add just a couple more key features today. So quadratic equations, you've seen them before. You have graphed a quadratic before. It is a parabola. It's going to be a U shape. Standard form, what is that going to look like? It's going to look like the form of y equals ax squared plus bx plus c, something you've seen before. Ultimately, they will graph a u each time you graph one of these. So, let's take a look at what the parent function of a quadratic looks like. So that would be something like f of x equals x squared would be our parent. Filling in my table down here, if I plug in -1 into here, -1 squared is 1, 0 squared 0, 2 squared that's 4, 3 squared is 9. So if I put those around here, 0, 0, 2, 4, 3, 9. Kind of do a graph sketch here. There we go. There is my parabola. It's my U shape. So looking at this is a continuous graph. Notice I can remember a continuous means start from here and keep going, right? Doesn't lift the pencil. This would be an even graph because it's foldable along the y-axis. My domain x values, so that's how far left and how far right can I get. Well, I can get forever to the left, so that would be negative infinity. And I can get forever to the right, which would be positive infinity. My range looks like I'm starting at 0, and I can hit at 0, so that's a bracket. Remember that? Bracket was when we were able to hit it. Maximum, there are no maximums, no locals or absolutes for that matter. Minimum, I do have an absolute minimum, and he is at y equals 0 at x equals 0, or the ordered pair 0, 0. I am increasing, well, it looks like, remember, increasing in intervals, these are your x values at all times. So I am increasing from 0 to infinity, and then I am decreasing from negative infinity to 0. End behavior is something we haven't talked a whole lot about. That's going to come back again in this. What's one of the things we're going to be introducing. So as x goes to negative infinity, aka as my graph goes to the farthest left, what is my y values doing? As I get really big negative x values, what's my y values doing? Well, they're going to positive infinity, right? Because this guy's going to keep going up. Then we're going to look at the opposite side of the graph. As x goes to infinity, so as x gets really, really big, positively, aka what's happening on the right of our graph? Well, we're going up to infinity, right? Now let's take a look at our x-intercept. Looks like it's 0, 0. And then we also have a y-intercept of 0, 0 as well. So that's what our parent function looks like of a quadratic. Of course, it's going to move around, it's going to do some shifting, stuff like that. So, parts of a parabola. Normally these are going to look like V's. They're going to kind of look like a V, but more of a U. There's two sides and a turnaround point. Now, this turnaround point is called your vertex. Same thing as what we called on a V. Now, you always want to see both sides of the parabola, just like how we always saw both sides of our V. So, got a couple of things to be aware of. You got some x-intercepts right here, right there, and right there. One thing we did not find on our absolute value graphs, however, you could have, what's known as your axis of symmetry. AKA, it's an imaginary line that we can draw through our parabola, and it would fold the parabola perfectly in half. AKA, it's the fold line, if you want to consider it. Where would the graph be symmetrical? We'll be identifying that. These will always be x equals some number equations, just because it's always an x equals graph, because it's an up and down line. Then I also have your vertex, aka your turnaround point. What we mean by turnaround, that's what means that I stop from increasing to decreasing, or vice versa. And then you also have another x-intercept / y-intercept would be also over there. So being able to identify some of the parts of the parabola are the focus of today. Some properties of standard form. Something we haven't talked about. Concavity, which basically is just a fancy term for which way does the graph open. If it's concave up, that's when a is greater than 0 in your equation. Because remember, we're looking at ax squared plus bx plus c. Now, these kinds of graphs are going to look like this. And I like to think of it as up like a cup. Alright? And then I got graph is concave down when a is less than 0. AKA I got a negative out here. So that would be a graph that looks like this. And to remember it, down like a frown. That's the only way I remember the two. Concave up like a cup, concave down like a frown. That's how I remember my concavity statements. Vertex, how do you find it? It's a little bit more difficult than when we were finding it with absolute value. What you need to do is find your x value by using this cool little formula. And yes, it does come from the quadratic formula. It's going to be negative b over 2a. That's going to give you your x value. To find the y value of the vertex, you're going to substitute the x value to get into the equation. So let's try an example here using our organizer. So the equation we're going to solve is f of x equals x squared minus 4x minus 5. That's what we're going to graph. So the very first thing, let's find our vertex. So I'm going to do my negative b over 2a, so that would be 4 over 2 times 1, aka 4 over 2, aka 2. So that's my x value of my vertex. To find my y value, I'm going to take that 2 and plug it into the equation up here. So I'm going to go 2 squared minus 4 times 2 minus 5. So 4 minus 8 minus 5, I get negative 9. So 2, negative 9 is my vertex. So I'm going to put that in the middle of my chart here, 2, negative 9. And just like when we were doing absolute value tables, you're going to want to put some groupies around that too. So I'm going to put a 1 there, a 0, 3, and a 4. Plug these in to get my corresponding y values. So that'll be negative 5. If I plug in a 1, I'll get 1 minus 4 minus 5, which is negative 8. 3, that'll be 9 minus 12 minus 5. Ooh, that's negative 8 as well. And you know what? 4 is going to be negative 5 as well. That's always going to happen as long as you find your vertex and you place it in the middle. You should get a perfect mirror effect around your vertex. Let's graph those dots here. So I got 0, negative 5, 1, negative 8, 2, negative 9, 3, negative 8, and then 4, negative 5. Nope, I put a dot at the wrong spot. I was wondering why that graph looked kind of off. There we go. 1, negative 8. Okay, so if I graph my parabola here, looks like it's going to do something like that, and something like that. Okay, so now looking at my vertex, I do know it's a minimum graph, right? It's going to be a minimum. because it is a valley. It would be my absolute minimum. My absolute maximum would be infinity. Concavity, we are up like a cup, so I am concave up. Axis of symmetry, aka where can I take this graph and fold it perfectly in half? So that would be like right here, right? See it right there? Drawing my dotted line in. There is my axis of symmetry, which is at x equals 2. That would be my axis of symmetry. End behavior. There's two end behaviors you need to look at on each of these graphs. So you're going to look as x is going to negative infinity. That means goes to. I want to know what your y value does. Well, as I go to negative infinity, aka this way on my graph, as my x's get more negative, it looks like my y's are getting more positive. So that would be positive infinity. And then I got as x goes to infinity. So you're basically looking on the left and the right of the graph. So as I go to infinity, it looks like my y value is also going to infinity. Let's flip back here. Y-intercept. Oh, it looks like my y-intercept was 0, negative 5. Now, how does one find that algebraic? How do you find a y-intercept algebraic? All you're doing is plugging in 0 for your x value. So we're going to plug in 0 to x. That will give you your y-intercept. So the equation, got to write it above here, otherwise I'm going to get lost. There we go. X squared minus 4x plus minus 5, plug in my 0. That's how I get my y value of negative 5. That's how you can find it if it doesn't fall on the graph perfectly, because sometimes you're going to get decimals and junk like that. But being aware that you can plug in 0 for x. Now, how do you find your x-intercepts? Because notice on our graph, they look like they're a little crazy. So, finding your x-intercepts. What you're going to want to do is either factor or quadratic formula. So, you're going to set the equation equal to 0. Basically, you're going to make y equal to 0, because that's how you find an x-intercept. So I got 0 equals x squared minus 4x minus 5. Looks factorable. A times c will give me negative 5. So I need two numbers that multiply to give you negative 5, but add to give you negative 4. Well, multiplies to give me 5. Well, just 5 and 1. Oh, negative 5 and positive 1. That'll give me a negative 4, right? So I can jump immediately to my factors since my a is 1. So it looks like I have an x values of 5 and negative 1. So ultimately, my x-intercepts on my graph should have been 5, 0 and negative 1, 0. Close. Not perfect, but close on my graph. Continuous, we talked about continuous. This is continuous because I can draw him continuously, don't have to pick up my pencil and move him. He doesn't have any discontinuities anywhere. Boundedness, remember there was a couple of options we had for that. We could either say that it was bounded above, bounded below, not bounded, or bounded, which means it was above and below. So if I look on this graph, it's definitely not bounded above, right? There's not an upper bound on this graph. There is a lower bound though. I can only get so low, and that low is negative 9. So I would say that I am bounded below. Okay. Domain, looking on my graph, I'm able to go all the way to the left and all the way to the right, right? No problems on our x values. So I got negative infinity to infinity for my domain. And then range, looking bottom to top. So lowest I can get down to is negative 9. And the highest I can get is positive infinity. So I got negative 9 to infinity for my range. Almost done here. We got increasing to look at and decreasing. Remember, these are your x values. Make sure you make a little note. X values. Okay. Looks like if I draw my car here, there's my car. Really good. I would be decreasing from negative infinity, because we're starting on the negative infinity on your x values, guys. X values. So I'm starting at negative infinity. I stop decreasing at 2, aka your vertex, aka your turnaround point. So I am stopping my decrease. I start at negative infinity and I stop at 2. And then I start increasing right at 2 and I keep increasing forever. So that would mean 2 to infinity for my increasing interval. And that's the end of this video. We'll do a couple in class as well, so we get some more practice together, so you can ask a couple of questions if you have any. But until then, see you later, Sabers.